Every so often the topic comes up of which data structures to use for different scenarios. Bjarne Stroustrup is often misquoted as saying that arrays are better than linked lists. This video will be comparing hash maps to array lists. Let's take a simple scenario of a lookup operation. Assuming you have a string, you want to find an integer value associated with that string. This would commonly be used to convert a name into an ID. Assuming we're just doing this in code and not using some external service, most experienced programmers would immediately select a hash map for this purpose. Hash map implementations exist in most modern languages, or are available as well-proven libraries. Some languages call them associative arrays, Python calls them dictionaries, and Go just calls them maps. It may seem silly to even consider an array list for such a purpose, because the major benefit of a hash map is that lookup time is constant, whereas an array list will slow down proportional to its size. But there are some peculiarities to that rule of thumb. If we make a simple array list implementation and run some tests against Go's built-in map, we see exactly what the rule of thumb tells us. The array lookup time increases with the size of the structure, whereas the map speed stays fairly constant. But something odd happens if we zoom in on smaller sizes. It's a bit difficult to determine the exact crossing point due to the noise in the data, but smaller than about 15 elements, the array list is faster than the map. This is true for the fastest, slowest, and average lookup times. This shouldn't be terribly surprising. The map has to hash the string value, then do string comparison to resolve hash conflicts. Since the array list only has to do string comparison, there's some crossover point at which the hashing is more expensive than just looking at each value. In this case, it seems to be somewhere around 15 elements. But the interesting data doesn't end there. If we look at insert speed, up to about 50 elements, the map and the array perform equivalently, although we see the array's performance start to balloon as the sizes get much bigger. The surprising part here is that the worst case performance for the map is roughly equivalent to the worst case for the array, even though the average speed for the map is clearly better. One might say that the insert speed is more predictable for an array list than for a map. Things get even weirder if we do some optimizations to the array list. Let's assume that we're getting our data from a well-designed database. In such a case, we know the size of the data before we create the structure, and we know that there are no duplicate keys. Optimizing for this, we see that the speed for array list inserts consistently outperforms map inserts at all sizes. Deletes tell a similar story to lookups. Deleting from a map is constant time with some variation, whereas deleting from an array list is clearly increasing linearly. Note, this graph is logarithmic. However, at the low end, we see the array list outperforming the map at sizes smaller than about 20 elements. Of course, raw speed isn't the only way to compare the two. Another consideration is memory usage. A convenient way to visualize this is with Platypode. As you can see, the map platypus is a good bit larger than the array list platypus. In conclusion, rules of thumb exist for a reason. In most use cases where the rule of thumb would be to use a map, the map will perform better than an array list. However, rules of thumb are not carved-in stone laws of nature. One place where an array list is preferable is with small list sizes, where the array list actually outperforms the map. Another case worth considering is any time that memory use is a problem, since array lists use memory more efficiently than maps. Finally, when the nature of the data is known before creating the lookup structure, optimizations can be made to outperform general-purpose structures. As always, it's important to test your code to see if your needs fall into a special case. Other factors, such as the nature of the key or the size of the value, may conspire to create edge cases as well.